fun, but if you ever do a guest lecture, you can do whatever you want. Like, you've got 1 hour and that's it. So I took my 1 hour and I milked it. It's great.
What did you do on it?
I swore a lot. I did. Well, I started off and I said, look, I've heard rumours that Mel said that I have a bit of a potty mouth. And I think I should just point out that she should go fuck herself. And once I did that, it just went from there, and their faces were just, oh my God. And at one point, they had this horrible formula. No, we had this, we're doing the sum of squares breakdown, and I said, look, don't worry, we normally won't ever ask you to actually calculate this by hand in an exam. And I paused and I went, oh, I don't know. Does Mel hate you or not? Has she given an indication whether she hates you as students or not? Because if she hates you, you'll be doing this by hand. But if she's really nice and likes you, you'll be fine. Because I knew that 2 slides later, you have the really horrible formulae. So I flicked to that and I went, oh, fuck, she hates you. Yeah, you're all fucked. You seriously are absolutely in serious trouble. If she's willing to put this as a slide for you lot, you are not just doing it by hand, but you're not even allowed to take your shoes off, do the counting. And yeah, it just went horribly. It was fun. I enjoyed it.
Did they learn?
Yeah, because in the jokes, I spent a lot of time making sure that, well, hopefully you were in the prac, making it very clear about what was important. Had they learnt it?
You know what it's like.
Nova's hard. I looked at the slides afterwards. I was chatting to Mel. We need to change the slides. The slides and they don't focus on the right things for that audience.
Well, Estro just described it as a 2-sample t-test with more than 2 samples.
Yeah,
which is fine, and they got that. But
yeah.
As soon as they say anything else, they're just like.
I did try and make the idea of why don't we just do lots of pairwise? So I talked about multiple hypothesis testing and the scenarios you use it in, but we show the breakdown, and I don't think they get what we're doing. So I talked to Mel, and we'll change the slides. But that's lecturing. You just slowly get better. Cool. So, am I recording this? I hope. Thank you. So, some housekeeping. We've got today's lecture, and then on Monday I'm going to introduce as sort of an aside some extra stuff, MapReduce, which is a standard way you do with big data. So we're going to have a whole thing on hash functions, MapReduce, that sort of stuff. That'd be useful because it sets up our final workshop. So this week we have a workshop on how to write an R package. The final workshop, if I can organise, I've now got access to Ronin, and I'm going to set up an Amazon cloud server for you all each, so you'll be able to log in and actually run a thing called Sparkly R. So this is how you do MapReduce in R while still staying within the R environment. So I have it all set up. If we can get it all done, what I will do is I'll meet someone to make sure I can set it up. You'll get invites to it. Make sure you've logged in and have that ready for the workshop. And in the workshop, we'll actually all spin up a machine, have a look at some basic data, and do some MapReduce type stuff on a big data set.
What is that?
That's the Friday of week 12.
Oh, going into the extra teaching week, John.
What? Why? No.
What?
Week 12's not the extra. Week 13's the extra.
Oh, shit. For some reason I thought there were 11 weeks in it.
No, we have 12. You've just done one of my courses before where like week 11's a bit of an extra teaching week. So discussing that, I'll put up a poll, but I was thinking, so MapReduce will be our last content area. So we've got 3 lectures spare. Now, one thing we could do is I thought that maybe we could have a thing that the last 2 lectures, we actually start to look about how do you, as a data scientist, find out about a method when you don't know about that method. So in that, we'll have it almost a workshop. You bring laptops, I'll bring a lot of textbooks, and over them 2 workshops, I will give you a method, and between yourselves, you will find out how to find out the information, find out the mathematics, find out how to implement it. So that's definitely one possibility. The last lecture probably will be just a revision lecture. Probably what we'll do is we'll work together to produce a mind map of all the material so you can see the connections between it. The other possibility is that next Wednesday, instead of having a workshop on a particular method and we all work on it together, I give you that as I come in here, you can come in and ask questions, etc. on your presentations. So I'll put a poll up and see what people want to do. So you can think about that. As I said, the exam is written. The exam at the moment has gone in. It is a 3-hour exam. If I remember rightly, there are 6 questions. So roughly, I'm thinking about half an hour. I've tried to set it so when we went through, me and the checker and did it, you should be able to do it in about an hour and a half. But I assume that it would be more like your 3 hours. So I sort of went through and went, I can do this in about an hour and a half. So I think it will take you about 3 hours.
You can do it.
Yeah. Gary's exam's a good starting point. The assignments are good starting points. The usual things, go through the material. The one thing to remember that will be different about this exam to last year's exam is 2 of the questions are more on implementation. So at least one I will give you R output and get you to use that output, interpret that R output. And another one, I will be giving you code and you will have to be able to interpret the code, etc. What I'm not going to ask you to do is write code. I think writing code blank without a computer in front of you is hard. And I'm not going to ask questions like, can you write the command to do this? It's more likely going to be, here are some commands, what are they doing? Okay? So make sure you feel comfortable doing that.
So we have to like remember a bunch of commands and what they do.
Yeah, but they'll say like tree of this tilde dot of a data set. What does it do?
Okay,
It's a
fine.
tree. Whereas
Yeah.
if you said, how do you fit a tree? I go, I don't know what the function's called.
Yeah, and that's what it is. Giving you code and saying what does it do, or interpret it, or use it is a lot easier because being familiar and looking at a command and going, yeah, as you said, it's probably doing a support vector machine, it's probably doing this, is a lot different than someone just blankly saying, what's the command to do a cross-validation trimming of a tree? In future years, there will be a practical exam. I actually think now I've taught the course, what would be better is to have one written exam with all the theory and stuff like that, and one exam where I go, you've got 3 hours, here's a data set, do this. So that's what I'll change in future years.
Would we have access to the internet to do that?
No, what I'm thinking of doing, because I don't want people to memorize stuff, is say you can bring in one R Markdown file that is less than a certain kilobytes.
That's clever.
Thank you.
That's
So that's Mel's idea. Well, her idea is in hers, she gives you a notebook at the start and says, in your PEC exam, you can bring in the notebook. I want to get people thinking about R Markdown. So now what you do is you go, you write an R Markdown file, so people can bring that in, you submit your R Markdown and your answers, and that way I limit it so people don't just paste everything in there, but it makes you, every time you do a method, go, what are the key things I need? Let's add a bit of information to help me. So that's what I'm still thinking of doing. Whether they give me this honours course again, probably not.
Depends on the cells, I guess.
The cells. Oh yeah, I'll talk about cells in a second, thank you for reminding me. What they are doing though is we're now introducing a 3rd year elective data science course, which will be in the 2nd semester, and this course will be stripped down and form that. So, thank you for mentioning the cells. The cells, well, I'd be really interested in your cells. First of all, if only 2 of you do it, I don't get the results. So as many of you to do the cells as possible is really, really cool. It means I can get feedback on what we did right and what we did wrong. Remember, you only improve education for next year by giving us good, honest cells. They are very important, especially the comments. So I want to say with the comments, one of the things I'm going to do is next year this course will become an undergraduate 3rd year course. I'd really like to know from you lot what works, what doesn't, what should stay in, what should go, etc. for a 3rd year undergraduate course. For 3rd years who, in the long term, won't have a lot of background mathematics.
Is it a maths course, the 3rd year one, or is it going to be?
It'll be a stats course. It will be, a prerequisite will be SHME, but we're changing the whole structure. There'll be people who will come through SHME in future years who won't have 1st year maths.
It's going to kill that subject, isn't it?
No, there'll be 2 cohorts coming through. Some of it will be trimmed back, but some of it, there will still be the theoretical statistics type course. But the problem is if we don't teach data science, other people will. And we believe that we're probably the best people to teach data science. They also believe they're the best people to teach data science. So
we're right, because we know that we're right. So
you're not completely right. I think we have to be careful. Anyway, so yeah, if you can give me cells, that'd be really, really good. If you can make sure you have enough.
How many people do you need to do the cells for you to get them?
proportion of the course, isn't it?
No, I think you need at least 10 people.
So pretty much everyone taking the
There's
class
11
needs
people
to
taking
do
the
it.
class.
And the fact is, they don't go, here's your results, just don't take them seriously. They're just like, less than a certain number, you just don't get them. Which means all your comments and everything go to waste, which is a real shame because CELTs are, the numbers, fine, they're great. You know, all the university cares about is broad agreement. But the thing that I care about is the comments. Comments are really good. They do actually affect how I teach. Hence, I now wear pants.
I was going to say, did your pants come in hell?
Yes. Cool. So let's continue our unsupervised learning. So I'm going to look at the EM algorithm here. So EM for expectation maximization. And you might say, well, that's not really unsupervised learning, but if you think about it, I'm going to motivate this with a very simple example. Imagine I've got this data set, and we can see that it's reasonably bimodal. We've got 2 peaks there. And what we think when you look at this data is perhaps there's some sort of underlying component. Perhaps this is actually a mixture of 2 components. So now you can see the sort of connection to unsupervised. You don't know which component this data belongs in, and what you're trying to do is you're trying to elicit the group membership from this data. But what we do is we're going to assume some underlying model to do that. So it's like a parametric unsupervised learning methodology. Okay. So let's say we've got this data. We've got some value y, and we notice it's bimodal. So we'd like to say that maybe this could be a mixture of 2 underlying distributions. So we're going to make it really nice. We're going to start off by assuming that the underlying distributions are 2 normals. So you've got 2 sorts of distribution. You've got the y1s, which is a normal with a mean of mu1 and a variance of sigma squared. You can see that I've assumed that we've got the same variance in each group to make it nice and easy. And then we've got y2 observations are n y2 sigma 2. And what we're doing, it's almost like, to get our observations, we'll think about our generative model. Imagine we're going to simulate the first observation. You get a coin and you toss it, which is our, in this case, our delta, our capital delta. And if that comes up positive, you go fine. You're from group 2, so you go and simulate from a normal with a mean of mu2 and a variance of sigma, or variance of sigma squared. If you didn't get the success on that toss of the coin, you come from the first group. So you've got this membership, which is denoted by your delta, and our general distribution, or y, overall is a proportion, a delta of them are from y2, and the remainder are from y1. So that's our generative model, how we're considering it.
How is the probability that delta equals 1 equal to pi, if pi is not a probability? As in, is that meant to be pi as in 3.14, or is that pi?
No, that's pi as in the Greek letter p, as in it's representing a arbitrary parameter that's a probability.
Okay.
Oops. So you can actually calculate your joint distribution. Your distribution is going to be written like this, where F1 is your PDF of the normal and F2 is your PDF of a normal. The first one is a normal with mu1 as its mean, and the second is a normal with mu2. And I got this mixture density by just using the law of total probability. I'm saying, what is the probability that y equals y? I add in the extra information about my delta. And so the first term is the probability y equals y given delta equals 0 times the probability delta equals 0, plus the second term is the probability. So it looks complicated, but it's just the law of total probability with conditional distributions. So first term, this is the conditional probability of y given delta equals 0. Second term, this is the conditional probability of y given delta equals 1. And then times by either the probability that delta equals 0 or the probability that delta equals 1. So from that, we can now write our likelihood. In fact, our log likelihood. That's all fine. But that's hard to solve because I've got a log of products and sums, and unfortunately, you can't just take a log. It's not a linear operator. You can't just separate this apart. Although at least one person foolishly, when it's doing some very complicated calculations, has done that. And then not just making a mistake, it's not the equivalent of just doing the dried macaroni on thing, and then went and presented these results to Gary.
Was it you?
It was me.
Yeah.
Yeah. Everyone goes, of course, the log of a sum is not the same as the sum of the logs. It's absolutely obvious. until you write page 3 into a middle of a complicated calculation, and that basic math just disappears out. And then you forcefully go in and you go, here I am, Gabby, and he goes, oh, bless, you've even got sparkles on it. I'll fuck off and do it right. So how can we deal with this? How can we make this problem nicer? Well, let's assume for a second that I actually knew the group membership. I knew for each observation whether it's in the first group, delta equals 0, or the second group, delta equals 1. If I knew the group membership, well, now it becomes really easy. You basically, the entirety of it becomes, well, you've just got two normals, and you know where everything is. So we're going to set in this idea that I have a latent variable, delta I, which tells me which group the ith observation is. Now, it's really nice. We've got just for each observation a Bernoulli type. So here's my standard probability mass function. You've got the probability when you're in the first group, with that nice indicator function of 1 minus delta I. So in this case, if on the ith observation, I'm in the first group, delta I will be 0. So the 1 minus 0 will be 1. You get the first term, and the second term disappears. So that will be your probability mass of being in the first group. You've got your probability to be in the first group, which is the probability of y given your delta I and your delta I. So you've set it up as what we call a Bernoulli random variable, and the same for the second group. This is really nice now. This is quite nice when I separate it. Now I can actually separate it into two terms. I've got 1 minus my delta I, the log of that term. And I could take this now and I could differentiate this with respect to pi, sigma squared, mu1, mu2, and get maximum likelihood estimators. Analytically, in fact, and we will do in a second. But we made a very big assumption. I went, assume that I know delta I, and we don't know delta I. But what you could do is you could go, right, I will start and I will just randomly go, I will choose a mu1, a mu2, and a pi I, and a pi and a sigma squared. If I did that, for each observation, I could say, what's the expected group you should be in? So if you actually guessed it, you could sort of go to this data here and go, well, anything towards the left is probably in group 1, and anything towards the right is in group 2. So if I have values of my parameters, I can calculate the expected group you're in. And in fact, I'm not going to do a hard classification. I'm not going to go, you're in group 1 or group 2. I'm going to give you a probability you're in group 2 and give you what I call responsibility. So as you get further and further to right, I'm going to give you a value higher and higher that you're in group 2, while if it's lower, it's in group 1. So let's do that. We don't know delta I, so we're going to use the expected value. We're going to call it gamma I of theta, which is also known as the responsibility. And it's going to be, in this case, the expected value of delta I given a set of parameters and the data. Now, obviously, I need to choose a set of parameters to start off with. I'll choose a set of parameters and I go, which group do I expect you to be in? And because our delta I is a Bernoulli random variable, we know that the expected value is equivalent to the probability. So it's almost saying, what's the probability you're in group 2? And obviously, we can take that and we can put them values in. We can place our log likelihood with the gammas. So this is what we're going to do. This is our algorithm. And it's going to come across as the greatest con stats ever did. The bigger con is there is no Kaiser-Sose, but thank you. Because we're going to cheat. We're going to say, start with a guess of your parameters. So you just guess mu1, mu2, sigma 1, sigma 2. Here I've separated them, we've assumed they're the same, and pi. So I just guess them. And then I go, now I've guessed them, I can go to each observation and go, what's the probability you're in group 2? Now, once I know which group you're in, if I knew what every group you're in by the thing we said before, I can now go and estimate mu1, mu2. I mean, to some extent, it's just going to be a weighted sample mean, a weighted variance. where I don't hard classify and say, right, these lot are in group 1, let's calculate the sample mean of group 1. I say we've got a soft classification, so I do a weighting. So, first of all, I calculate in step 2 my expectation step. That is your probability that you're in group 2 for each individual observation. Maximization, I took that log likelihood, I differentiated it, I solved it. That's what you've got there. And you see that mu1, that is just the weighted sample mean of all the observations. Imagine I hard classified, and all the ones in the second group, I made that a 1, and all the ones in the first group, I made the 0. That would be now the equivalent of just doing the sample mean of everyone in the first group. mu2 hat, that is the weighted sample mean for the second group. What I've done with the sigma squared is I actually did a weighted variance calculation. And I did the Remel equivalent, which is why it's n minus 2, not n. I knew you were looking at that and thinking, oh, that should be n with the maximum likely estimation. But I did a Remel. I just did a standard simple one. All it matters is I took all the observations and I weighted them to take into account whether in group 1 or group 2, where the values are going to have a value between 0 and 1. Finally, I calculate the pi. So, okay, I've got this slightly better parameters. Now I've got slightly better parameters, I can go back and reclassify everyone to say, are you in group 1 or group 2? Once I know which group you're in better, I can get better estimates. Once I get better estimates, I can go back. It's a con. You started with nothing and said, if I knew the parameters, I know which group you're in. If I know which group you're in, I can get better parameters. And I just keep doing it again and again. That's the EM algorithm, that's all it is.
Why is that okay?
First of all, you can show with a very complicated proof that it actually converges to the truth.
Okay.
Now, I know it's a complicated proof. I once did the proof. It took me approximately 2 days to go through the proof to understand it. I wasn't quite sure of the final step. I walked into my supervisor's meeting and I said to Gary, I've been spending 2 days working through the EM algorithm. He went, oh, that's a nice one. I'm doing the proof and I'm pretty well there except for the last step. And he went, and it'd be a moment that made me realize that I am human and he is a god. He went, let me just redo the proof. On the top of his head, he then redid the entire proof. He didn't look it up, he didn't check anything, he just walked over to whiteboard and did the entire proof of the EM algorithm, explained it better than any book I'd read, just like that. Now either he knew that I would get stuck and he had already prepped it, which with Gary could be the case, or he is fucking awesome. And in either case, he's fucking awesome. And that's the point in your meetings where you suddenly realise that he will always be better than you and you will always be an idiot compared to a guy who can just do he would do it now. Someone would go, can you prove that like you? And he'd go, yes. And then an hour later, the proof would be on that board.
Do you have to think about the last step at least?
No. No. It's Gary. It was the point where I suddenly went, fuck, I am never going to be that good. So
this proof will not be the exam?
No, that's... Unless, of course, I hate you. Have I given any indication that I hate you?
Wait for the next slide.
Oh,
all right.
So now let's actually show it working. So, I'm going to set up an initial guess. I'm going to assume that, so you say, what can be initial guesses? Sometimes you can take your means to just be the first quantile. I just looked at the values and I took a small number and a large number for my mu. To get my standard deviation, I just took the standard deviation of all the data. I guessed, I went, well, I just assume that there's an equal amount in each group. So I set my p, which is my pi, equal to 0.5. So I put this in a vector of parameters and I made it a named vector. So we could just pass parameters around in a single vector. So expectation step. So expectation is going to take my data and my parameters, theta. It works out the top of the calculation, which is our theta pi. So that goes to the theta and finds the element named pi. So that's the probability of the mixture population. Times my d norm. And I did y mean equals theta m2, sd equals theta s. Then to get the bottom, I'm going to take that term and add the other part of it. And then I return that. So that gives me my responsibility. So you can see, and what you'll generally see if I plot it, I didn't, is that as y gets larger, you find that your g, which is your responsibilities, gets larger as well. And you should have values between 0 and 1. M step. Fine. I've now got my G's and my Y's. First of all, I calculate N, which is the number of observations. Then I calculated M1, which is my estimate of the means in the first group, which is just to some extent, it is just a weighted sum, where I weight on 1 minus the responsibilities. M2 is now the weighted, sorry, not the weighted sum, the weighted mean, is the weighted mean for everything in the second group. And then S is that square root of that big thing, which is just, I'm combining all the variances and just using the group membership, the soft classification, to weight it. Then I return all of them as another named vector. So here's my updates. You notice that my first group, I went 1, is now shifted up. My second one, which I had as 10, is shifted down with the means. The standard deviation is now 1, when before it was 2.11, so that shifted down. And my pi has gone from 0.5 to 0.7. Just repeat. This is a bad bit of R code. Why is it a bad bit of R code? Just to make it easy, I have used a bind rows. So what I'm doing is I take my vector of thetas, and each time I create a new one, I just add it onto the bottom. Unfortunately, remember, if at any point you're writing code that will take a vector and keep adding things to the end, most languages don't just add it to the end. They go, wait a minute. They take whatever vector you've got, they copy it across into a new vector with your new point at the end. So all the time you're writing new memory. It's slow. What you should do is if you know how many cores it's going to be, you should pre-allocate your memory and then just do the counter that moves down. I just wanted quick dirty code. So I start with results. I set the first value, my old value, to infinite. Nicely, R has a built-in inf. Also has a negative inf in case you need it. 4 times, and then I just say each time look at the last results of my parameters, and these results look at the squared Euclidean distance between them. If that's greater than that, keep going. So off it goes. At each step I grab my data, I do the E step, then I do the M step, then I add the results, and I just keep going.
Does R not have a built-in thing to say do this function to this vector until it converges? I just would have thought that'd be a thing that they'd have.
Not that I know of. In what? Yeah, no, not that I know of off the top of my head. I must have always been sort of like. You mean the step where I do the sum of the squared distance between them?
Well, no, just like run a given function on a vector until it converges, right?
Yeah, no, I'll have to look now.
This is just a feedback, right?
Yeah,
It's just an efficient way of doing what you've just done.
yeah. I have to look see if it's built in. I've never seen it before. Every time I've done it, it's always been create your own wrapper function around it.
Yeah, okay.
Here's the results. I can now reveal that the truth was the mean of the first group was 4. The mean of the second group was 8. The standard deviation is meant to be 1. Didn't quite get the answer right on that. I'm not quite sure. And you see in a second that the built-in does it a lot better than mine. So I do need to go back and check my calculations because I did that n minus 2. I tried it with just n to see if it makes a difference, but I think I need to redo my calculations of my variance term. But the pi was 2/3. It's actually, I think I set it to 0.3 and 0.7, so it's getting that about right. So the means it's good. The pi and the s is not quite right, but you know, it was quick, dirty code.
Oh, so you only did it for what, 6 steps as well?
Yeah, it's converged really quite quickly, but I could do it for longer. So let's think about the general thing, what we're doing. So the original idea of the EM algorithm was in a very early text, and it was all about missing data. It was actually there to deal with missing data. How can you impute missing data? And then someone discovered that often you can use it to help in maximum likely estimation of certain scenarios, where often by choosing data that's missing, you can make your problem easier. So you think about our previous problem. If we know which group each observation is in, it becomes a very easy problem to solve. Our group membership in that case is our missing data. And if we knew it, great. If you don't, it makes it a hard problem. Another one they use it a lot is in things like genotyping, and there's a lot of scenarios where you'll suddenly see the EM algorithm appear. And the thing you should always ask when you see the EM algorithm appear is, what's the missing data that they've added that's made the problem easier to deal with? So let's think about this. So it's often used for likelihood problems, but it can be used for other problems as well. But the whole thing is that by enlarging the sample with some latent, unobserved, or missing data, we make the problem easier. So consider we've got data Z, and it's got log likelihood L of theta given Z. And we're going to denote the missing data by Zn. So there's extra data we could add in, and the M is just for missing. So you consider we could have some complete data T, which is our observed data Z plus the extra missing data. And here's the general EM algorithm. You would start with initial guesses for your parameters, which are called theta hat 0. So there are initial guesses. In the expectation step, what we're going to do is we're going to create a thing called Q. And notice it's the expected value of the complete log likelihood. Now, in our particular case, if you take the expected value of the complete log likelihood and just do that expectation, it comes down to just looking at the expected value of the delta I. But the proper definition is in not terms of that responsibility, it's in terms of the expected log likelihood of the complete data, given your observed data Z and your initial guesses. The maximization step is you just take that and you optimize it to give you a new estimate of your theta hat, which we'll now call J plus 1 because on the J step. And you can do that with maximum likelihood estimation, as in differentiate it to equal to 0. You can just optimize it, but you're just taking that Q heuristic, which is the expected value of the complete log likelihood, given your data and your guesses, and you're just going to maximize it, and you just iterate the steps.
So what's theta prime? Theta.
Theta prime is to say that you have your thetas in there. One you're going to maximize over, which is your theta prime, and then your theta hat. So it's the idea that you've got some values in there that are from the previous step. They are known values you're plugging in, and your free variable in this case is the new theta. So it's just to separate and say you've got this theta prime, which is your value you're going to vary to maximize. So your free variable in this is your theta prime, and your locked in values are the previous estimates, which are your theta hat J. Often we do something called the SEM, the conditional expectation maximization, because, and we've already done that indirectly, if I remember rightly, is if you look at this, when I calculated my S, which M do I use in that? Do I use the values from the previous step, or do I do the values I've just calculated? And in fact, often what they do is when they come to the maximization, they maximize and then they condition the maximization on the other values they've already got. So you're doing this condition. You're not maximizing M1, M2, and S all at the same time. You're going, given all the information I've got, let's maximize mu1, well, my estimate. Then I will maximize the second one. And then when I got to the third one, I actually used the best estimate I already had, which in this case, you can see I used M1 and M2, which is not the values I had from before, but the values I've just calculated. So you do this iterative conditional. It's called SEM, conditional expectation maximization. Or do the bleeding obvious. So how do we actually do it? Well, unfortunately, a lot of the times what you want to do, your mixture model is not nice, and you have to sit and do the calculations. I personally have a complete dislike from the EM algorithm, not because Gary made me realize I was human and he wasn't, but it is slow. In my PhD, I rewrote my expectation maximization for my problem. I rewrote it at least 10 times in 5 different languages to get it fast and never achieve speed. I did it in lots of different languages to try and do it. And there's a lot of tinkering, I must admit, is hard. But if you're lucky and you think you have a mixture of standard distributions, then there's actually a package that will do it really nicely, the mclust package. And the mclust is all about mixtures of multivariate normals. So there's the library mclust, I call that. I then fit it with just the mclust dfy, so I just give it the data and off it goes. I don't need to give it initial values or anything, it does everything. And in the end, it fits this. It says your best bet is to have, it considers two variance models, one where you have the same variance, one where you have different variances. And this one has come back and said your best one is one with an equal variance. And it returns your log likelihood, your n, your clustering, how many are in group 1, how many in group 2. It gives you your mixing probabilities. It gives you your means and your variances.
If it says there are exactly 700 in group 2, why is the probability of being group 2 not 0.7? So it split the clustering perfectly.
Yeah, because it's doing a hard clustering at that point. And the calculation would be from the maximum likely estimation,
And round it.
but then it does a rounding hard clustering at the end.
Is that
That's what
rounds?
it's doing, yeah. I've never seen anyone do an EM where you do a hard clustering. You could definitely consider doing a hard clustering type thing, or your weightings will disappear. But I don't know whether it would have the same asymptotic behavior in the proof, because you lost that continuity. If you do plot DFM y equals BIC, it will give you your BIC on your y-axis and the number of components. And you can see it's trying both models here. It's trying one where you have equal variance and one where you have different variances. And it's just returned the one with the best BIC. So let's look at a more complicated one. We're going to look at diabetes. So diabetes, remember there's two sorts of diabetes. Diabetes mellitus and diabetes insipidus. Do we all know the difference and why they're called that?
Which one's one, which one's two?
No, diabetes insipidus is where your ADH, your antidiuretic hormone, is not working correctly. The interesting thing is one is called insipid diabetes and one is called sweet diabetes. Because one is about your pituitary glands not working, you're just producing lots of urine. The other diabetes, the one that you all know, is diabetes mellitus, which is about sugar concentrations. So lack of insulin. Without a lack of insulin, insulin's one job is to take glucose in your bloodstream and push it into your body cells. What happens when you have diabetes, you don't have enough insulin, or the insulin is not, the cell's not sensitive enough. So your blood glucose goes up. Your blood glucose has to go somewhere. It comes straight out in your urine. Hence you have sweet urine, hence diabetes mellitus. This we're looking at is diabetes mellitus. That's how they used to test. You would be weeing a lot and they go, you're weeing a lot, are you? Let's have a... Yep, that's mellitus. Unfortunately, it was years before they had either the test or the ability to treat it, so I don't know why they test it. I mean, just go, you got diabetes, like, we don't give a fuck. We're not going to drink your fucking urine so we can give it a Latin name. But obviously they did. So, here we have three classes that we actually know the information, but we have our glucose levels. This is the area under the curve under a glucose tolerance test. So you basically give people high level of glucose, you measure their glucose blood levels over a certain amount of time, and you calculate the area under that curve. The same with the insulin. The SSPG is the steady state plasma glucose. I'm just telling you all this so I can show that when it comes to medicine, I know stuff, unlike baseball where I know diddly squat.
Steady state. What does that mean?
Basically, when you do the test, you wait to see where it settles out and doesn't vary. Because your glucose goes up and down when you have meals, you want that, what you sometimes call the fasting glucose. What's your glucose state when you haven't just had your Mars bars?
Ooh, a Mars bar right now.
Yeah, I shouldn't have said that, have I?
It's mean.
So here's some scatter plots of the relationships, and I've just coloured so you can see what we've got there. But imagine I didn't have the different groups. Imagine I just had this data and I wanted to look at it. And you can start looking at these scatter plots, and these don't look like nice Gaussian, bivariate Gaussians. But we just read it. So I've taken that data frame, I've removed the column of the identifiers, and I said, go find me what we've got there. We know we've got 3 groups. We could actually, do the calculations. We'll have a look in a second. But go and do mclust. And it then does this. So I've done the same thing. Now, all these EII, VII, EEI, VEI, etc. are different variance models. And you just have to look them up. So one thing you do is go, I've got Gaussians, and they're all going to be spherical Gaussians. That is, you're going to have the variance in both directions for your x and y will be equivalent. In this case, it's 3 dimensions, so you have a 2-dimensional sphere of your Gaussian noise. You can have spherical Gaussian noise, you can have all the same or different, you can have them rotated, etc. The one we ended up with is the best, is this one here. We've got a 3-component, which agrees with what we know, and it's the VVV. What it's saying is you can have different sizes for your Gaussian noise, they can be rotated, it's the ultimate freedom in the different types of Gaussian it has. It's the multivariate dimensional version of just going, we can have, each group has its own variance term. In this case, each one has its own complicated sigma, which should be your variance covariance matrix.
Well, the best one is the one that lowest BIC?
The highest BIC.
Highest BIC, yeah, okay.
And you can grab stuff out. So here is the proportion within each group. So 0.53, 0.26, 0.19. So that's your clustering. I didn't do the summary because it just took multiple slides. So I've just grabbed out individual bits. You can get out your means. So here's your mean for group 1, group 2, group 3. Remember, the means will be down the columns for each of the groups. Here's all your different variance covariances, one for each group. So they've had a different variance covariance and they've not completely unconstrained. And you can see that when you look at our actual plots. So I've done a plot here where I've done each scatter plots, pairwise scatter plots. I've shown the 95% confidence interval for each Gaussian, so you get an indication of that structure of the noise. And you can see that the means are all over the place, but for example, the blue group, especially if you look at the insulin SSPG, so the bottom middle one, there's a nice almost spherical type noise structure on the blue group, while you've got this very spherical, ellipsoid type noise structure on the green group. So it's giving you ultimate freedom in that VVV. But you don't have to do all that. If you think about it, to do that, you'd have to do all the calculations for each possible combination and put that in. It's doing all of it for you. Unfortunately, it wouldn't do my problem in my PhD. So I got to do all this myself.
What was your problem?
I was looking to identify gene profiles for pluripotency in stem cells. So,
Yeah, and basically when they hit the ball, it goes over the fence as a home run.
yeah, thank you very much. All we really want to do was your stem cells, when you first made them, are pluripotent. They will make any cell you want. Then after 3 days, they become multipotent. So, for example, your bone marrow stem cells will make any blood cell you want, but they won't make a kidney cell. And we wanted to know, out of all the genes we looked at, which are the ones that are associated with pluripotency. Because then what you can do is you can go to someone who's got kidney failure, you can take a cell from their bone marrow, which is easy, you can switch on the right genes, it becomes pluripotent, and then you can say, now make me a kidney cell.
Can you do that?
We're getting there.
Okay.
So then you can now do, and the good thing is if you do organ transplants from yourself, you don't reject it.
Makes sense.
So that's it. And the problem is we said, well, what does pluripotency look like? And they went, oh, that's fine. It will be high, high, low, low on gene expression. So I found stuff that would go high, high, low, low. But then what I did is I actually fitted it and I would go, here's the posterior probability that you're matching that profile. Then I showed them the genes I got and they went, yeah, but we expected we'd get SOX2, which is a gene. So I went back and I looked at SOX2 and it sort of went high, medium, low, low. So I went, okay. I went and wrote code that you could put in any constraints. It would deal with equality, so I had equivalence testing in there, so I could say, these 2 points have to be equal, these 2 points have to be equal, the mean of these have to be different. So I'd set up all these constraints and run it. So I set it up in a general form, so they would just come and say, I need this profile, And my code will look at all your genes and spit out and rank them in a posterior probability of being associated with that profile. I hated it. So it seems to work quite well. What I did do finally is I actually compared the classes with what we've actually got. So on the bottom you've got the truth. You can see that it's good at getting normal. Normal is pretty good. Out of all the normal ones, it's classified a couple as group 2, but most of them it's managed to grab as group 1. So it's pretty good. It's not bad, it's not perfect. But remember, normally you wouldn't have the truth. You just see this data and say, could it be actually written as a mixture of a particular distribution? And EM will let you do that. Cool. Whew, that took longer than I thought. Any questions? EM algorithm. So this week we have a workshop on our packages on Friday. Next Monday we will have our last content lecture, which will be on hash functions and MapReduce, which is basically what you need to know if you're going to start doing big data. Wednesday, we're either going to have a help session for your presentations or a open workshop on how you go about dealing with methods when I haven't taught you it. Any questions? Cool. I can see I've excited you all. So for Ashley, Ashley's got her I hate you with all my soul.
Yep.
Except for the bit I saved aside for Matt. Thank you all. See you all on Friday. And as I said,